So today we are going to discuss about continuity of trigonometric functions. We have recently seen in the previous videos that these functions are differentiable on their domains. For example, sin x and cos x are differentiable on R, on the entire set of real numbers. Tan x and secant x are differentiable at every real number, both of them, except at the odd integer multiples of pi divided by 2, because these are the real numbers where these functions are not even defined. Elsewhere, wherever they are defined, they are differentiable. Similarly, cotangent function and cosecant function are both differentiable on this set at every real number which is not an integer multiple of pi, because these are the real numbers where these functions are not defined. And that is why, because they are differentiable, automatically they are also continuous. Let's recall the result that tells us that. And that theorem is this, theorem 1 of section 2 part 1, which basically tells us that differentiability implies continuity. If a function is differentiable at a real number, then it's also continuous there. So by this result, sin x and cos x are continuous on R, tan x and secant x are continuous on this set. You do understand this notation, right? This just means that from the set of real numbers, we are removing these real numbers. That's why this minus sign, it's set difference. And cot x and cosecant x are continuous on this set, at every real number other than the real numbers n pi, where n is any integer. And now, how does this fact, this continuity of these 6 functions on their domain help us? Because of this, for these 6 functions, we now have this fact that if we calculate the limit of, say, f is any one of these 6 basic trigonometric functions, if you want to calculate the limit of f at some point c, then it's enough to just evaluate the function at that point c, provided the function is defined at that point. And we are going to use this to next see some limits. So let's see that. So we see example 10, and here we are going to use this fact. So the limit we have to calculate is this. It involves trigonometric functions, but it's not simply just one trigonometric function. So limit of tan x at some point, it's not like that. It's a combination of trigonometric functions. But anyway, we have this fact. So from this fact, what do we know? We know that the limit of secant x at x equal to 0 is secant 0 because of this continuity and because of the fact that secant 0 is defined. Okay, at 0 the secant function is defined. Similarly, you can also see that at 0 the tangent function is defined. So the limit of tan x as x approaches 0 is also equal to tan 0. But that alone, of course, does not allow us to do this. But what allows us to do all these things in such a straightforward manner is should I say, are the limit laws. The algebra of limits that we saw earlier, that you can add 2 functions and to calculate the limit of the sum, it's enough to calculate the limits of the individual functions and take their sum. So by that algebra of limits, and also the fact that if you take the composition of 2 functions, if you apply one function and then on that you apply another function, there also you can apply limit. So by those rules, you can actually write this. So essentially what you just do, you replace x by 0 and then you just calculate the value. Secant 0 is 1, tan 0 is 0. So you have square root of 2 plus 1 as the numerator and cos pi as the denominator, and cos pi is minus 1, so that way you get the limit as minus root 3. So next we see other limits calculated with theorem 4. So we go back to theorem 4, which gives us this limit. Limit of sin theta divided by theta is 1 as theta approaches 0, and you also know that here theta is in radian, then only this limit is true. So we are now going to use this limit to calculate some similar limits, And the thing here is that this equation holds no matter how theta is expressed. What does it mean actually? It means this. Limit of sin x divided by x is equal to 1 as x approaches 0. Just like this one, and in fact it's from here that we have this. So here theta is just x, so as x approaches 0, theta approaches 0. And we also have this. Limit of sin 7x divided by 7x is also 1 as x approaches 0. In this case theta is 7x, and here also as x approaches 0, so does theta. And we also can have this. Limit of sin 2 over 3x divided by 2 over 3x is also equal to 1. In this case theta is 2 over 3x, and you can clearly see that as x approaches 0, so does theta. And based on these observations, we next have some other examples. Example 11, and the limit here is limit of sin 2x divided by 5x. It's not 2x anymore, but of course x approaches 0. So we make it 2x, and to do that we write the given function like this: 2 divided by 5 times sin 2x divided by 2x. So that after cancelling this 2 and this 2, you have 5x in the denominator. And then of course, because this is a constant, it does not depend on x, so it goes outside the limiting process, and you are left with this limit. Limit x tends to 0 of sin 2x divided by 2x, which by now you know very well is 1. So that way you get 2 divided by 5. So in this way, if it's not in that form, you have to turn it into that form and do the required adjustment with that. So this is part A, and then we have part B, which is this. Limit of tan 2x divided by 5x as x approaches 0. So we do not have sine now, but of course a sine and a cos are there in this tan. So what we do, we write this thing like this. So in the beginning itself, the moment we write sine 2x, we arrange for a 2x below it. Originally we do not have 2x here, so we take that 5 somewhere else, and the extra 2 that we have written here, we adjust that by writing a 2 here in the numerator as well. And do not forget, we still have cos, I made a mistake here. It's not cos x, but it's cos 2x. Won't really affect anything, but what is wrong is wrong. Alright. So next what we do, of course the limit will get distributed over this individual functions, individual factors, and because 2 divided by 5 is constant, so it comes outside the limiting process. So this equals the limit of this sin 2x divided by 2x times 2 divided by 5 times the limit of 1 divided by cos 2x. You already know that this first limit is 1, and the second limit is also 1, but exactly why is that 1? That is because the limit of cos 2x as x approaches 0 is equal to cos 2 times 0, because the cosine function is continuous and the function 2x alone is also continuous, so their composition is also continuous. We already know this fact, that the composition of two continuous functions is continuous, and that is why this cos 2x function is also continuous at x equal to 0. So the limit of this function at 0 is just cos 2 times 0, which means that it is cos 0 or 1. However, here we are not actually looking at the limit of simply cos 2x, but its reciprocal. So you apply the quotient rule for calculating limits. If the limit exists and is non-zero, then the limit of the reciprocal of the function is the reciprocal of the limit. But what is the limit of this? 1, and its reciprocal is also 1. So that way we get 1 here, and the final answer is 2 divided by 5. So that is part B. And then there is one more example as well. Next we have example 12. So this time we do not see that the variable is approaching 0, but let's see the function. The variable is t and t is approaching pi divided by 2, and the function is sine of t minus pi divided by 2 divided by t minus pi divided by 2. So at first it looks very complicated, but actually it's exactly this limit in disguise. Once you recognize the fact that you can just treat this t minus pi divided by 2 as a single variable, your job is done. And say that variable is theta. It is a variable because as t changes, t minus pi divided by 2 also changes. So what happens if t goes very close to pi divided by 2? Theta will go very close to 0 because it's just this difference. So that just means that we can now write this limit in terms of the new variable theta, like this. As t approaches pi over 2, theta approaches 0. And this becomes sine theta and the denominator becomes theta. But then we already know what this limit is, what its value is, it is 1. So that way we have this. So you may encounter many situations where initially it looks very complicated, but once you recognize that it's in the form of a known limit, then you just have to reduce the complexity by doing this kind of stuff. So if you do that successfully, the job is, it's already there, it's done for you. You just have to recognize the correct thing. And this is where this section ends. After this, exercises will start and that we will solve in the next week. Tomorrow we don't have any video, and according to the new schedule that you may find in the community section, from the next week we are going to do 2 videos per night. So see you next week with this new schedule, and on Monday I think we have number theory, and with that something else is there. Okay, I can't remember exactly. So see you next week with those things. Until then, this is me, Lucifer, from A Mathematical Room. Have a nice day.